Pierre Agostini is from the Ohio State University. So please welcome, please join me in welcoming Professor Agostini.
Thank you. Good morning, everyone. And okay, the title of my talk is the genesis of an attosecond pulse trade. It has nothing to do with trades, but we'll see. Okay, if some of you have never heard the word attosecond before, it's a very short time. It's billions of a second. And so one natural question that could arise is this series of, from second to nanoseconds and femtoseconds and attoseconds and more is infinite. Is it possible that to divide the time indefinitely like that? From a physics point of view, I would say that that's doubtful, because first of all, it takes more and more energy to produce those short pulses, and at the end we'll hit the Planck time, and that's an absolute limit. We are still very far from that time, but it's probable that the series is not infinite, and you cannot divide the time indefinitely. So, in this lecture, I would like to tell you about the physics of rabbit, and then I will tell you about an application of those attosecond pulse trades, and especially time application on double ionization. Okay, it's quite obvious that if you need to make an attosecond, then you need two things. First of all, you need a very short period for the light. And this means high frequency, and this means that you have to go into a domain which is soft X-ray and XUV or soft X-rays. Then what you need is a coherent bandwidth which is large enough to support the attosecond pulses. And this is a condition that must be fulfilled. So the harmonics that Anne L'Huillier talked about before seems to be a perfect candidate to produce those pulses. First of all, the frequency is high, and it can be up to 100 times the infrared frequency of the lasers. And then the bandwidth is quickly very wide, and so all the qualities are supposed to be here. So, indeed, back in 1992, those two guys, my old friend Kyoso Farkas, and his co-worker Chamath Todd, calculated that if those harmonics are in phase, if they are phase locked, it's say. And then in the time domain, that would correspond to a sequence of periodic pulses of very short duration. Unfortunately, at that time, this calculation by Anne and co-worker seems to show that the phase were not at all as hoped, but there was looking like random, absolutely random, and so except perhaps in the cutoff region where there are no photons at all. So, yeah, I come back to this question a bit later. Okay, then I have to introduce you to the above threshold ionization process. And for that, I will start with Einstein photo effect that was mentioned already. So Einstein has the idea that light is made of photons, and not of a field, but of photons. And the photons have a specific and definite energy of h nu, the product of the Planck constant by the frequency. So an electron can absorb or emit photons, okay, integer energy of photons. And now if the photon energy is large enough, then you can liberate, you can free one electron from the potential well in which it is. Okay, so this is well known from all the students and the high school students, I guess. The kinetic energy of the electron which is freed is the difference between the photon energy h nu and the potential energy the electron is kept by in the atom or in the solid or anything. All right, then that was the time of Einstein, 1905. But in the 60s, in 61, the laser was invented by Mayman. And actually, it was possible to ionize an atom with photons which were smaller than IP. And then you just had to pile up a number of photons. For instance, here, the kinetic energy is equal to 3h nu minus IP on this graphic. So the study of this MPI, so-called MPI, multiphoton ionization, started in Russia at the Lebedev Institute, and there are a number of papers from the mid-60s about that. Okay, and then I come to the above threshold ionization, or ATI, and it was, you know, by measuring the kinetic energy of the photoelectrons, it was immediately seen that electrons are more energy than predicted by the Einstein photo effect. And by the energy of the electrons could be that energy minimum 3 h nu minus IP, for instance, in this case, plus another photon or two other photons. So you could see that as peaks in the photoelectron spectra. So, how to measure the phase? The phase of the harmonics is the thing that is the key to attosecond pulses. And so, how to measure those phases? First of all, you need a nonlinear optics process. I'm not proving that here, but I ask you to take my word for it. The problem was that harmonics were not strong enough to do those multi-photon or nonlinear optics processes. So the solution was to mix the harmonics with a strong laser, and this could result easily in two-photon ATI or two-photon ionization. So we have now this case of two-color, two-photon transition. One is with a harmonic or with a photon which is large enough, and then we have ATI, that is the atom absorbs one photon more, but one photon from the strong laser. So we could have also more complicated things like that, where we have three colors to start from, the two consecutive order harmonics, and one photon being absorbed and one photon being emitted. All right, that's the key of the measurements we have done. And in 1996, those three theorists from Paris, Vignard, Tayeb, and Mackay, calculated that if you have an atom which is ionized by two colors to start from, right? Two consecutive order harmonics, then you should have two peaks, one for each of these colors. And if you mix those two colors with a laser, then the atom can absorb two photons, one photon from harmonics and one laser photon, or absorb one bigger photon from the harmonics and emits one photon. And since we know that those harmonics are only odd order harmonics, they are separated by twice the laser frequency, twice the frequency omega. And if one absorbs one photon from the laser and the other emits one photon from the laser, you added up to the same energy. This energy, gives rise, of course, to an interference. And okay, I'm sorry for the equation, but the result of this interference is that the amplitude of the middle peak, which is called the sideband, is given by this simple mathematical formula. And in this formula, the frequency is the frequency at which this sidebands oscillate, and the phase difference, which is the thing that we are looking at or looking for, is this factor here, delta phi q. So it's enough to change the delay and measure the amplitude of the sidebands to determine what the delta phi q is, and to determine the phase of the harmonics or the phase difference of the harmonics, and to check if whether or not we have attosecond pulses. On top of this delta phi q, there is a small correction that had to be calculated at the time, and I'll come back to that in a second. Okay, how do we implement the theory in an experiment? Okay, this is, I'm not going into all the details here, but the important thing was a mask, which was dividing the beam, the initial beam, into two parts. Then we had a couple of glass windows which could be oriented and which introduced between the two beams an attosecond delay, a delay with attosecond precision. Then there is, of course, the jet where the harmonics are created. And then there is something which I called here a pinhole, which is just a hole in a piece of metal. And this has a very important role, as we will see immediately. Okay, this is the first measurement of the harmonic phases in our experiment 20 years ago. And so what you see here is the spectrum on the top box, a spectrum with no infrared, without this laser photons. And so what you see are the peaks corresponding to the harmonics. Okay, then we introduce the laser, we superpose the laser to this harmonics beam, and we have more peaks in the spectrum, and those are the sidebands in between each of the initial peaks, and the amplitude of the sidebands changes with the delay. All right. So once we have that, we can plot the different sidebands that we see on the spectrum as a function of the delay, and we see oscillations as predicted by the mathematical formula of Vignard, Tayyab, Mackay, and from these oscillations one can derive the phase of the harmonics, the phase that would decide whether or not we have attosecond. So it turns out that from these phases, the phases are very well behaved, not at all the random things that was predicted by Antoine and Maciek, but from the amplitude measurements and from the phases measurement, then one can reconstruct the time domain of the pulses of the light, and we had this train. I mean, train meaning here a sequence of periodic pulses, and the pulse duration was at that time something like 200 attosecond. That's much longer than, okay, that was 20 years ago, right? Now, probably Ferenc will talk about that, but the pulses have shrank to 43 attosecond, right? I think that's the last number I saw. Okay, the question is, does this, that's the calculation of Anne that we saw a moment ago, contradict that, I mean, this behavior which look completely random, and this one looks pretty nice, so is there a contradiction between the two? Okay, I'm not going to talk about the details which have been already described by Anne, but the question is this angular distribution of the two amplitudes that interfere and that make the phases look absolutely random, that can be really solved with a very small and cheap things, which is probably the cheapest thing in our experimental setup. And so this is a pinhole that isolates one of the two amplitudes that creates the problem with the randomness of the phases. So this is done by just because of the angular distribution is different, and if we put somewhere in the beam this very simple gadget of a pinhole, then this suppresses completely one of the interference amplitude, and from there, if the interference is suppressed, then the behavior of the phase is fine. One word about the small correction. You remember perhaps there are two terms, the harmonic phase difference, and there was this small correction. The small correction has made a terrific career in the past 10 years or so under the name of photoionization delay. That's the technique that was used to measure the time delay between, the time delay taken for the electrons to be removed in a photoionization process. Well, I put some titles there, but you can see in the last one that, okay, in one title there is already Attosecond coming, so the future is coming here. Okay, now I guess I have a few pictures that have been provided by Philippe Balcou of the laser we used at that time. That's not much of a picture, but at least I've been guaranteed that is authentic. Okay, those are the two windows that were used in the experiment and in the setup that we used to control the delay between the two beams. So it's, the two windows, this is a window clearly on the left. On the right, there is a small part of a window, the small central part is a window, which has exactly the same thickness as the other one, because it has been taken from the other one. And so, yeah, this is again a courtesy of Philippe Balcou, and Amel Zahir, and CNRS, and Celia. So this is not really the usual, the authentic one, the old one, which have disappeared, but it is a replica which is exactly the same and which has been actually used in an experiment. So I like to show some picture of our students at the time. I mean, Elena, Thomas, and Pierre, Marie-Paul, which were, I think, in the audience somewhere. Philippe Balcou is here. This has provided a number of things. And one special mention is about Müller, Professor Müller, who not only invented this setup that we have used in the experiment, but also invented this wonderful acronym of RABBIT, whose explanation is in the title of this paper, which came out 1 year after the first one, and is a reconstruction of attosecond harmonic beat by interference of two-photon transition. Okay, then you know everything. Okay. Then I would like to talk a little bit about an application. And the subject of this second part is the strong field double ionization. Okay, first I could show you, okay, that's show and tell. A modern atom beam line at Ohio State. So you see tubing, and well, the electron spectrometer is down there. The laser is somewhere in another room, and so the laser beam is coming through those tubes. It's under vacuum. Everything is under vacuum because all those harmonics are XUV or XUV or soft X-rays. So naturally now everything is automatic. In the first experiment we are turning the glasses by hand to start from. So yeah, all the time. Now it's completely automatic, and what you see here is a sequence of measurements. And first of all, the laser are kilohertz repetition rate, so it's much more accurate and precise now. Okay, so double ionization. I mean, once you have extracted one electron for an atom, so you have an ion, and if you try to extract a second electron, then the work you have to apply to the atom is about twice the first one. So it's predicted from that would be much more difficult to extract the second electron than to extract the first one. But okay, an experiment or several experiments in the 1924 showed that this was not at all the case, and that ionization of a double ionization was not that difficult. So one of the explanations was provided by those guys, I mean, Paul Korkum, Ken Kullander, and Ken Schaefer. Ken Schaefer is here somewhere. And the idea is that if you extract one electron in the presence of a strong field, this electron can be accelerated by the field and then stand back to the nucleus where it started from and extract another electron by a E2E process, by sort of billiard balls, right? So the probability of this element is much larger than what expected by, say, multiphoton processes, perturbative multiphoton processes. Okay, now the experiment that has been done in Columbus at Ohio State by those students and under the direction of Lou DiMauro is the following. Okay, first we have this strain of attosecond pulses that we can, absolutely precisely delay with respect to the optical cycle of the laser. So we can decide exactly at what moment, at what time within the attosecond pulse duration the electron will be ejected. And then we can detect or observe the return time of these electrons, the time that separates the emission from its return to the nucleus by observing the doubly charged ions. And from the knowledge of the departure time and the return time, we can reconstruct the electron motion exactly. So that's one example of how you can use those attosecond pulses to control and observe electrons' motion in a strong field. Just a quick look towards the future. So far, all attosecond pulses are created by laser, a visible or infrared laser, and harmonics. Now, the problem with the harmonics is that they are not very powerful. I mean, they are sort of weak. And to observe nonlinear processes with them, we have to mix them with a strong laser. Now, at the linear coherent light source, X-ray free electron lasers, which is this this small setup of 1 kilometer long or something. I'm finished. People have already found that they are able to create isolated attosecond pulses with gigawatt peak power. So that's at least a factor 10 above the current harmonics at the moment. So maybe the future of the attosecond is not in the lab and not with our laser and harmonics, but with this LCLS X-ray free electron laser. Okay. Thank you.